All right, welcome. We are now getting an introduction to power series. A power series looks like something like this. So we have 1 plus x squared plus x cubed, and we just increasing the power. This is called the power series. So in this specific power series that we're looking at, this is an example of a geometric power series, because we are increasing by the same r value. We are multiplying each term by x to get the next term. So if it converges, what must be true about x? Well, we looked at geometric series, and the number that we're multiplying by has to be less than 1. So the absolute value has to be less than 1 for it to converge. If we had equal to 1 or greater than 1, we knew that it diverges. So we need to look at some specifics with power series. Now, a power series is, you can think of it as a infinite polynomial. So we can take some polynomial and create a power series that would mimic that polynomial. We're going to get really deep into this later on, but for this first video, I just want to go through a couple examples of how to write a power series given some specific information. Okay, so this infinite polynomial here, this one we just talked about, we could say that this is defined by the function 1 over 1 minus x, and we can write it as a series, as a power series. So we can write an infinite polynomial as a series. Okay, that's what we're going to be doing. Now, this can be tricky and this can be confusing, but once we get into some Taylor and Maclaurin polynomials and some different power series that we're going to look at, it should start to make sense. All right, so finding the power series for each function, and we're going to show 4 terms of the infinite polynomial, okay? And then we're going to write a series in sigma notation. And then we're going to find this thing called the interval of convergence, which we'll talk about in a little bit here. All right, so this first function, 1 over 1 plus x, so we can think about a power series. So, well, not a power series, a geometric series. When we talked about that, we said if it does converge, we can find what the value is using our formula. We have the formula the a over 1 minus r. So this is in this format. We can say that this is a geometric, okay, power series because of the formatting. So we can identify our a value, okay. We can identify our r value. So the a value is on top, and the r value is what's being subtracted from 1 on the bottom. Well, it's a plus x, so we have an r value of negative x. Okay. So now we can go ahead and write our polynomial. So our f of x in our power series, the function we're going to write to mimic this, is 1, so we start with the a value, and then we're going to multiply each term by our r value. So 1 times negative x, we would just get minus x. And then if we multiply this term by negative x, we get plus x squared. And then again, we get a negative x cubed. And we can just keep going forever. Now, we could write if we wanted to. Well, I guess we can't really. I mean, we could, but we're not going to right now. We could write our nth term, but until we get comfortable with this, we don't need it. So now we're writing our power series in sigma notation. So we have our a value of 1. So remember the format: a times r to the n. So we have this. Okay, so a times r to the n. We're going from n equals 0 to infinity. Okay, another way to write this, you don't have to have this, but we could write this as a -1 to the n. So our alternating series, we could have an alternating geometric series here. So we could say that this is times x to the n. We could say that. These are going to equal out to be the same thing. All right, so we gave our polynomial in 4 terms. We have that. We have our series in sigma notation, and we want this interval of convergence. So we're trying to find 3 things here. All right, so an interval of convergence. So real quick, and I can go more into this later, but the interval of convergence talks about how accurate our polynomial is. So the polynomial that we've created, this infinite polynomial, is an estimation, essentially. So there's error in it. So the further we get out, the more terms we write, the closer it's going to get to the original function. But if we just stopped at 4 terms, and we graphed this polynomial with 4 terms against this polynomial, and I'm going to make another video showing you this, but it's at the center, so this function, we need to think about where it would be centered, but we'll get in more into that later. At the center, they're going to be identical, okay? And as we move out from that center, if we look at a graph, so say we're at x equals, x equals 0. So say we're at 0, 0 on the origin, which we may or may not be, but just think about this. At 0, 0, those 2 functions, the one that we were given, the one we created, give the same y value, so the same f of x. As we move away, both sides, so as we move to negative infinity, positive infinity, the function starts getting less accurate. Okay, the y values are going to be a little off. So we're trying to find out where these 2 functions would overlap perfectly. So this is called the interval of convergence. And again, we're going to get in more into this later. So all we need to know for the geometric power series for this video is the r value has to be less than 1. The absolute value of the r value has to be less than 1. Okay, we talked about that when we looked at our geometric series, okay, a couple sections ago. All right, so what do we need to do? We need to set up in our situation here. We just said that the r value, so our negative x, the absolute value of that has to be less than 1 for this to work. We need to find the interval of convergence. That's what we do. We take our r value, the absolute value of it. We need to see where would be, what would cause this to be less than 1. So now we have to solve our inequality. So we know that that's just x, right? So those are the same thing. Absolute value of negative x, absolute value of x, less than 1. And if we remember how to solve absolute values, we have to split this up. We have to solve the inequality by splitting this up into x is less than 1 and x is greater than negative 1. So we switch that sign of that number and we flip the sign. So x has to be greater than negative 1 and less than 1. So we can write our interval of convergence. Okay? So put it together. So this is our interval of convergence, and we'll get more into how we express the interval of convergence later. Actually, the radius of convergence, we're going to talk about that. But for now, we can leave it as an inequality. All right, let's do 2 more examples for this video, and then I'll make another one. So let's go back to red here. All right, so we can look at this. We have a number over 1 minus 2x, so 3 over 1 minus 2x. We can identify this as a power series. We can write a power series for this. So a value is 3, so the number on top. And then the bottom, r value, 1 minus r. So our r value is 2x. Okay. So let's write a power series. Actually, we're just going to write the first 4 terms of our infinite polynomial. So we always start with that a value. And then we're going to multiply that by our r value. So 3 times 2x would be 6x. And we just keep multiplying by 2x. So 12x squared and 24x cubed. And so on. All right. So writing our sigma notation. So we are going from n equals 0 to infinity of a times r to the n. So there's our sigma notation for our power series. Now we are finding the interval of convergence. So again, our r value, the absolute value of it, has to be less than 1. So absolute value of 2x is less than 1. So again, we're going to split this. We're going to say 2x is less than 1 and 2x is greater than negative 1. I'm going to solve these out. X is less than 1/2 and x is greater than negative 1/2. So we can write that. Okay. So there we go. That's the interval of convergence. And then last example here, h of x is 1 over 3x. So at first glance, this might not look like a power series, but it is. So it's geometric because we can write an a value of 1. We have a number on top. And then on the bottom, so over here I'm going to write what the bottom would look like. We have 1 minus 1 minus 3x. Okay, so that 3x is equivalent to this. So I would subtract 1, I would get 0. Subtract a negative 3x, I would get positive 3x. So I just rewrote it a little bit. So that's what that looks like. Okay, that's our problem. So a value is 1 on top. And then we're subtracting this r value. So our r value is 1 minus 3x. Okay. Power series notation, sigma notation, we have the sum from 0 to 8, not 8, infinity, of a times r to the n. Now, do we need that 1 out front? No. I'm just showing you that it's in the same format. So I went a little out of order here. I wrote the power series first. Let's write the polynomial here. before I forget. Polynomial would be 1. We have the a value 1, and then times r. So we're going to multiply by r. So we have this quantity, and we can just write it like this. And we're just going to keep multiplying by 1 minus 3x to each term. So the next term would be 1 minus 3x squared. Okay, quantity squared. Next one would be quantity cubed. And so on down the line. All right. And then interval of convergence. So we're taking our absolute value of the r. That has to be less than 1. And we're going to split it up. Okay. So we can do this in 2 separate ones. We could put it together. We've learned how to write a compound inequality and solve it back in your days in algebra. So if we have this, we could have, flip the sign, flip the number. Okay, so we solve these out. I'm going to get a little bit into these problems here, but subtract 1. So if we subtract 1, so this is less than 0, and then we have subtract 1, we have a x is greater than 2/3. Okay. That's it. So ask any questions if you have them. We'll go over these next several examples in a couple more videos.